Today we start the last two chapters for this semester, and since these two chapters, chapter 6 and chapter 7, are really telling the same story, just from different angle, or maybe they are rather a continuation of the same story, we are going to treat them together, so there will be only one quiz for both of them at the end. So, the chapter is about thermodynamics. Thermo means connected to heat, connected to temperature. Dynamics means how the system is changing. So now there are generally two different types of thermodynamics. We already discussed this before, just for remaining. One is the phenomenological one. And one is the statistical one. And we already discussed a bit the difference between these two thermodynamics when we were discussing gases. But just for remaining, phenomenological thermodynamics operates with terms like pressure, volume, temperature, mass, and many others similar to describe the system. Now we are going to introduce few new terms like internal energy, enthalpy, entropy, Gibbs free energy, Helmholtz free energy, and maybe some other too. We are going to introduce these new terms to describe, again, even in a better way, the system. The statistical ones, as we already said, generally operate on the positions x, y, and z of many particles, on their velocities, of particles, on the average of velocity square, for example, and many other terms like that describe virtually the same. In chapter 6 and chapter 7, we'll be working primarily with this one. Only one time, to understand what really entropy is, we will go to the statistical description of thermodynamics, that you can count entropy on your fingers. Well, maybe not enough fingers, but yeah, it would be easy. Good. The basic word in the thermodynamics is system. System is the set of molecules or atoms that you are studying. Around system, you have everything else, what is called surroundings. Everything together makes universe. So now, the first assumption here is that the surrounding is huge comparing to system. It means if system sends something out, the system will change, but the surrounding will not change because it's so big that you can forget about this very, very, very small, tiny change. So surrounding has always constant mass, constant volume, constant temperature, constant pressure. But system, these things can change. Okay, now there are two different types of system, well, maybe more than this. One of them can exchange energy. And these are called not isolated systems. Next one, cannot exchange energy. And this is called isolated system. The next one can exchange mass. And this is called open system. And the last one that is explicitly studied cannot exchange mass. And this is called closed system. These are virtually the four most important types of system that we are going to study. If you have a problem to solve, usually it starts. You have a closed system, you have a not isolated system, or so on. But to be honest, this is the most popular that's going to happen, isolated one and closed one. These two. The other may happen. Good, let's go further. Now we are going to discuss what type of terms we are going to use. I just give the glossary first, that later when we come to it, will be P, pressure. T, temperature. M, mass. V, volume. What else? As W we usually say work. As Q we usually say heat. The next one is U, is internal energy. Next one is H, enthalpy. S, entropy. Next one would be F, which is called Helmholtz. It's called Helmholtz free energy, or just sometimes it's called free energy. And the last one is Gibbs free energy. And sometimes people, they just say Gibbs energy. Later we are going to introduce such things like what's it called? Molar heat. And similar thing, CV. And I'm not sure it's everything. There may happen that there will be something more. Let me just have a look. No, looks like it's everything. Good. So we can continue. These are the terms we are going to use. Now some of them may seem strange to you. I assume that you know the following. Pressure, temperature, mass, and volume. Well, even if you don't understand what they really are, I sometimes don't understand. You at least have some feeling about them. I also assume that you know what it means work, and you also know what it means heat. Again, difficult to define, but we are going to discuss it. Now, for internal energy, we are going to have some discussion probably in the next class, so I just keep it blank for now. Enthalpy, Helmholtz free energy, and Gibbs are defined as follows. As I give you these things at the beginning of the course, that you can remember it very easily. Later when it comes separately, it's more difficult to remember. You are going to start with internal energy. If you are going to add PV, you are getting enthalpy. You are going to subtract entropy times temperature, you are getting Helmholtz free energy. If you are going to add PV, you are getting Gibbs free energy. Well, everybody sees that closing this one is just minus TS. So it's very easy to define these functions. H is just U plus PV. F is U minus TS. And G is U plus PV minus TS. Well, very often this is also written as a H minus TS, or this is also written as F plus PV. These two we are going to define later when time comes for it. Okay, let's go further. So we already know system, we know surrounding. Now we are defining something time-dependent phenomena. So processes, when the system is changing, many things can be changing. Temperature can be growing, pressure can be getting larger or smaller, volume can be changing, reaction can be going on, phase transition can be going on. But very often to describe these different processes we are going to use the following word. So we are going to have isothermal processes. Isothermal, it means a process when the temperature before and after is the same. So process at constant temperature. Iso means the same. Thermal temperature, the same temperature. The next one is going to be isobaric. This is the process at constant pressure. Next one, isochoric. This is the process at constant volume. Next one is the adiabatic. Adiabatic one can be defined in two different ways. One of them is that there is no heat exchange. This one can be also said in other way, no entropy change. So isoentropic process, in other words. This all can be said as a cyclic. This sounds strange when I say everything, but it really means that at the beginning, the temperature, pressure, and volume changed, and at the end, they came to the same point. So at the beginning, the temperature and volume and pressure are the same like at the end. Also, other state functions are the same. When I say state functions, I mean other functions like entropy, enthalpy, Gibbs, free energy, and so on and so on. So everything is the same. This is a cyclic process. Next one. Exothermic. And a complement to this, endothermic. Exothermic, it means the system gave outside some heat. So the energy of the system went down. So change in the system energy is smaller than 0. Endothermic, it means the system took some heat from outside. So the system's change in energy is larger than 0. So what we are doing now, we are just learning a new language. Since for solving exercises we are going to use these things, we are saying the reaction is exothermic, and I'm expecting you to know what it means. So I'm giving you the new dictionary on this first class. Next thing, different type of work. One is called expansion work. And this one is going to be equal V equal P change in volume. And we should stop here for a moment, because if you think that the volume is getting to be larger, it means the system did work. After the system did work, the energy of the system went down. So the volume is negatively proportional to the energy, the minus sign. And we have different types of work, like extension. This is the change of length, and this is the work done for this. So for example, if I take a piece of metal and I start stretching it, it requires a lot of power, but I can stretch it. After stretching, it will be longer. So to do this stretching, change of length, I need some work. Next one is just gravitational work. Next one is electric work. When there is a flow of charge, delta Q, between the difference of potentials, phi. And then there is a lot of different type of works that sounds strange, but turns out that you still require energy to do this type of work. And one, for example, of them is surface extension. And this is going to be equal work needed for this use the same letter A. This may be for entropy. So this is the change of surface. And this is surface tension. And you can ask me, what is this? This sounds very strange. Well, we discussed it in the last class. We said that if you have a liquid, the perfect shape for the liquid is a sphere, because a sphere has the largest volume at the smallest surface at the same time. Okay. But now, if something happens to this, if you squeeze it, the volume will be the same, but the surface will go larger. Because every other shape than a sphere has larger surface. And this is exactly the equation telling you how much work you need for doing such a process. And it's kind of easy to calculate how much is the change of surface, and the surface tension is a property known for every liquid. Okay. First law of thermodynamics. By the way, how many laws of thermodynamics there are? 4. Good, good. You know one more than me. But I'm glad that you studied it in the high school. The first law of thermodynamics said that for the closed system, you remember closed system? System that doesn't exchange mass with outside, only energy. So energy exchange is okay. So for the closed system, the energy exchange can be either 0, and we call it isolated system, or the energy change, internal energy change, can be equal to the heat exchange between system and surrounding and the work done by system. And this is called not isolated system. However, some people would just call it closed system. Even if closed system also may mean this. And you studied the first law of thermodynamics in high school, I guess. Right. Okay, in this moment I may say we finished chapter number 6. There is nothing more in chapter number 6. I mean, there is some small, simple calculations there. And we are going to do some simple, small calculations out of this. Good. Let's discuss maybe now what is the internal energy. And take situation number 1, when the system is just one atom. If our system is one single atom, the internal energy of this system is only the kinetic energy of this atom. but somebody may say, hey, that's not maybe clear, because that's true that the atom can be traveling on X, Y, and Z, but maybe the electron can be arranged in different ways inside this atom, and that's true. So the internal energy of the atom is not only its kinetic energy, but it's also its electronic energy. And what this means is just the expectation value of the Hamiltonian with the wave function of this atom. Starts to be complicated, right? Because we said in the previous class that it's very difficult to solve this Schrödinger equation even for simple 2-electron atoms. So this term is going to give us some problems. This one would be probably very easy to deal with. Okay, let's go further. System is one molecule. System is one molecule. What is the difference between one atom? It still can translate X, Y, and Z translation. So the internal energy of this system would be again 1, 2, m but now the system can also rotate. So we have rotational energy of the molecule. There would be 1, 2 over yeah. But again, if you have atoms inside a molecule, these atoms can be vibrating. And these are some quantum numbers for this. Turns out that for rotations, there are also quantum numbers. The system cannot be rotating with any speed omega. It can be rotating only with special types of omega. And we are not going to discuss this in details, but unfortunately, this equation is not a very good equation. This is just an approximate one. Turns out that there are also the energy of vibrations, and there is also the electronic energy on the top of this. Wow. For one molecule, the internal energy has already very complicated definition. What happens if you have two molecules? Okay, then you would have that the total energy is equal the energy, internal energy of the first molecule plus the internal energy of the second molecule plus the interactions between molecule 1 and 2. Well, usually electromagnetic, electric interactions between these molecules. But you see that the number of terms is getting huge already for two molecules. And there is another thing. We said that we are going to discuss phenomenological thermodynamics. But I came inside and I'm speaking about the electronic energy of a single molecule. That's bad, because if I go to the system of 1 million molecules, I have to know electronic, vibrational, rotational energy of every molecule. Disaster. There's too many numbers. And these terms, the connecting terms, are going to be very, very complicated. That's why phenomenological thermodynamics is saying the following. It's not important what is U. What is important is the change in U. Why it's important? Because then it's nice. If our system at the beginning is moving at 1 meter per second and at the end is moving 2 meters per second, we can say that all the other parts, electronic, vibrational, rotational, didn't change. So when you calculate delta, they just cancel. And you have only the change of energy coming from the change of process. So this is important one. And this is not important. Some of you may be unhappy with this solution. I'm unhappy myself. I think it's just too easy giving up, saying it's not important so we don't study it. And this is important so we only concentrate on this. Well, but that's how it goes. If you go to the books of thermodynamics, it will say U is a sum all possible internal energies of molecules like vibrations, rotations, translations, interactions. But it's never defined by equation. It only says that what really is important is the delta U. What time is it now? Once again? 10:53. Good. We're going to have maybe 10 more minutes of class, then we are going to have a break and you are going to write a quiz. Okay, so let's continue. So we already said that the internal energy is not so important for what we are going to say further. So we are not going to define it further. We could possibly, but the equation would be much more complicated. We just stick to this one. We don't want to know what U really is. We want to be able to calculate the difference between two different systems or two systems in two different states. Good. We discussed already what are the different types of works. Now we should discuss what are different types of heat. Usually people consider as such three different things. What is heat? It's difficult to define, to be honest. Because when you think about heat, something has high temperature at the beginning, and at the end the temperature goes down. So the random movements, thermal movements of the body, exchange with the thermal random movements of the outside, of the surrounding. So now heat tells you how this exchange was going. Okay? So the one typical way is convection. Well, let's start from conduction. And to understand what conduction really is, you should imagine a box with molecules. There is moving around, hitting the walls like that. And now there is outside, and outside also has some molecules. And if these two molecules meet in this kind of collision, the molecule that has higher energy is going to higher and lower energy, they kind of average. It may happen that it goes opposite, but the probability of going that way is larger. That's why people usually discover. Okay, that's maybe a good moment to discuss it. Yes. Let's say we have molecule 1 and molecule 2. Molecule 1 can have speed V1. Instead of speed, I'm just speaking about energy. So can have energy 1 or energy 2. That is higher. And molecule 2 can have, again, energy 1 and energy 2. That is lower. Now this one, let's say the value, numerical value is 1 and numerical value of this is 2. Similar here. Now I know that total energy of molecule 1 and molecule 2 is equal to. What are the possibilities? The possibilities are, there are 4 of them. First one, there are first one is that the molecule 1 energy of molecule 1 is equal to no, that's maybe not a good one. I should introduce 0 to forget this. We'll do it later with the entropy. Anyway, we are going to study this. So, what is the conduction? Conduction is when the collision between the body inside the system and the body outside of the system is going to transfer the energy outside. So that one that is having higher energy is going to put the energy out. Or if this one has higher energy, temperature outside is higher, then the temperature will go inside the box. This is typical normal way of transfer of energy as heat. Random collisions of molecules in the surrounding and in the system. So this one is just collisions. Next one is called convection. And this is strange. This can be defined as extra fluid or extra liquid motion. And every of you have seen convection before in your life, but you maybe just don't realize it was convection. Okay. I first draw you the situation. When you take a pot and you put water inside, and you put it on the stove, for a long moment nothing is happening when you observe the water. But after some time you start noticing that the surface of the water or the inside of the water is not homogeneous anymore, but something starts happening, like different patterns appearing, different shapes. This is exactly convection happening. Extra motion, extra moves of the liquid. Now I'm going to explain you why it's going to happen. Now when the heat is coming inside the water, the first layer, I call it the yellow layer, has higher temperature than the next layer. So temperature of the yellow one is higher than the temperature of the red one. It means that the yellow one are moving faster, right? This is the typical conduction mechanism. Nothing new, just by collisions. But now, since these move faster, at the beginning they were occupying some volume. Now they move faster, the volume is getting larger. This is similar like for gases. If you heat gas, the volume grows larger. For liquids happens the same, but it's very small. Okay? So it means that the yellow one have now larger volume than they had when the temperature was lower. So what they're going to do, they're going to push the red one out. So the red one gets extra heat, but because of the change of volume, not because of the temperature transfer. Okay? And this is called convection. So the red one starts traveling, it's random traveling at different directions. And that's exactly what you can observe when you see the heating one. Some small wires appears, wires, strange things inside. So that's the convection one. And finally, the third way of transferring heat is radiation. And radiation is easy. This is just exchange of photon or exchange maybe of electron, I don't know. It can be different things, but usually exchange of photon. But you also know that in the radioactive radiation, it doesn't have to be photon. So I just underline it saying that usually photon, but can happen something else too. Now, sign convention. Energy goes to system. We are usually using plus. Energy comes from system. We use minus sign. Last thing, anybody knows, hand up. Perpetuum mobile. 1. Okay. Perpetuum mobile is a toy or a system that if you push it once, it will be always working. Never stops. How do you say in Chinese? There is no word for this. Okay, I mean, this is not English, this is Latin. And mobile in English means moving. And perpetuum in Latin means always. Or continuously, rather. No translation for this in Chinese? well, so many hundred years were spent by physicists for looking for perpetuum mobile, a system that you can push and it will be always working. But finally, the first law of thermodynamics shows that there cannot be such a system. Because every movement, you know that change in internal energy is either zero, but then if there is zero, there is no moving at all, everything stays quiet, or the change in the internal energy is the work plus heat. Turns out that the heat is always positive unless the speed of movement goes to zero. It means that there is no system with zero work that would be moving, because this one is always positive. So the system must be moving, doing some work, and that's why the energy of that one will be going down and down, which is of course impossible because there is always a lowest limit for every system in the internal energy. So this perpetuum mobile is an impossible system. And that's a good moment to finish this class.